I'll be sure to start the recording. No, recording is in progress. Awesome. All right. Howdy, y'all. My name is Dr. Rob Parks. I am the Deputy Director here at George Mason Observatory. And tonight we're going to have a somewhat unusual or irregular evening under the stars. Unfortunately, normally we have, I shouldn't say unfortunately, we typically have a speaker prior to our telescope tour. And so tonight the speaker is going to be me, although speaker probably is better, I probably should say rambler, because what I'm going to be doing is I'm going to be showing a planetarium program called Stellarium, which is free, and you can find it at stellarium.org. So if you're interested in doing what I'm going to be showing, feel free to download it and play with it. It's free. Like I said, it's a free program. And I'm going to be talking about the types of things you can see in the night sky tonight. And then we're going to be highlighting images of those during our telescope tour in the second half of this event. The sky right now is rather cloudy. So it might, we're going to wait and see. While I'm going fiddling around with Stellarium, we are going to basically just keep an eye on the weather. Right now, it is too cloudy for us to actually open up the dome and take images of the night sky. But we will be, regardless if it's closed or open, we will be showing you images taken primarily by our students of celestial objects using our telescope. So with that being said, let me move on. Let me give my normal introduction. And so the observatory has been around for about a decade. It was added to Research Hall, which you can see in this slide here. The telescope was placed, it was at the top of this silver tower on the outside of Research Hall, and we have a control room on the roof, as you can see there. And we can control the telescope at that location, or, and this is primarily what has happened, particularly in the current day and age, we can do so remotely, like we're going to be doing tonight. Our GTAs or graduate teaching assistants will be showing you the telescope in the comfort of their own home or wherever they happen to be at this time. And so what we have around these images on this slide are various images that have been taken using our telescope, again, primarily through student efforts. Owen, one of our friends of the observatory, he has been doing some amazing work in astrophotography, and I believe most of these images were taken by him. And they are nebulae, galaxies, moons, planets, that sort of thing. And actually, he broke our previous record. I'm already going off on tangents. He actually broke our previous record of the farthest thing that we have ever actually observed. And that, I believe, and I think Kevin can correct me on this, but I believe it's something like 3 gigayears, 3 billion light years away.
Yeah, that sounds about right. I'll double check that though.
But yeah, so he was able to, and eventually he's making the image nice and pretty. It's a cluster of galaxies that are 3 billion light years away from us. That kind of gives you an idea of sort of the distances that we can obtain here using our telescope. Now, this is obviously the evening under the stars. We only have, this is the second to last, this is the penultimate episode, as it were. We have one more talk in 2 weeks. I believe that is April 24th. One of our own is going to be giving that talk, William Matz. At the moment, I do not know what the source of that talk is, but I believe he works with supermassive black holes, so it should be a very interesting talk. These events run where typically a speaker will speak from 30 to 45 minutes, and then we would have a Q&A session for about 10-15 after that. And then finally, we'd have a 30 to 45 minute guided tour of the observatory. If it's clear, we would open the dome and actually take active images of the night sky. But if it is cloudy as it is now, we will keep the dome closed, but we will show you object images that have been taken using our telescope, and our GTAs will give you loads of information about the telescope itself and how these images are captured. If you're interested in the observatory or the astronomy events, or essentially astronomy research, astronomy public outreach, astronomy events happening in the Fairfax region, I would highly encourage you to sign up for our newsletter, The Moon, or the Mason Observatory Outreach Newsletter, where we write stories about space news. I think we have a Constellation of the Month segment. We also highlight research here and students that are participating in that research. So it is a wonderful tool, or it's a wonderful free newsletter that will also allow you to explore the observing options for public events that the Northern Virginia Astronomy Club puts on every month. So there's usually half a dozen public nights where you can go to a far darker sky than ours and be able to visually look through telescopes with them. If you're interested in helping us from a more financial standpoint, I encourage you to become a patron of the observatory. Sorry, my cat is distracted. I encourage you to become a patron of the observatory. We are attempting to greatly expand not only just our research arm, but also our public outreach arm. We are, and in doing so, we need some assistance from the public, because these projects take man hour or people hours, they take resources. And so any help that we can get in order to bring astronomy, not just at George Mason, but around the area itself, would be greatly appreciated. And you can support us at various different levels, from star all the way down to Big Bang. And here's a list of a few objects, or a few of our donors. Now, this is not a one-person show. Like I said, my name is Rob Parks. I'm the deputy director here. Dr. Peter Plavchen is our director. Kevin Collins, who is on the line tonight, is one of our observatory graduate teaching assistants. M. Thunyapong is another. He is also an observatory graduate teaching assistant. And then we have the Friends of the Observatory, or PHOTO, student organization. They actually had a night, I believe it was last night, where the club had full reign of the telescope. They were able to point it at whatever they wanted, take images of whatever they wanted, and they do this on a semi-regular basis. So far, it's been typically about once a month or so. So if you're interested in taking more of a hands-on approach to astronomy, particularly with our instruments, and you are a student of George Mason, I highly encourage you to get in touch with Jonathan or PHOTO. He's our president, and join that organization. All right. So now we are going to transition into sort of the public talk tonight. But if you'll indulge me for a second, I need to free my cat from it being trapped in a mattress. Hey, you, dummy, come out of here. Yes, you, get out of here. Last chance. Come on. Don't sniff around. Just come out. You're holding up the public. Last chance. All right. You're going to be stuck in there for like 2 hours. Oh, no. Come on. Get out of there. Sonny, get out of there. Well, you're going to get stuck. Hope you enjoy that 2 hours in there. All right. Sorry about that, folks. So let me share. That's all right. Sonny will be fine. It's plenty of air. Let me share my other screen. So we have, let me actually also pull up the chat window. Chat. So if you have any questions about, I hope you can all see the stellarium that's on the screen. the Stellarium program that I have on the screen. If not, please definitely let me know. If you have any questions about any of the topics that I'm going to go over, again, please let me know and I will address them as best I can. So this is what the night sky is going to look like in approximately 2 hours, around 9:14 or so. And what you see is one of the most prominent things that you'll, if it were not cloudy, one of the prominent things that you'll be able to see is the moon. And right now the moon is, and I apologize if I give anyone motion sickness in doing this. Let's see. Is the moon, and we would see it pretty much like this, where we'd see it not quite full. It is.
Sorry, Dr. Parks. It looks like the Stellarium window isn't actually moving when you click to drag it. We're still looking southwest.
Okay, because right now I'm looking at the moon. Is there a lag? What is going on here?
Now we see the moon.
Oh, I have a feeling this is going to lag quite a bit. So let me, all right, that's shared. All right, so you can see the moon. You'll probably have to let me know what you can actually see. So the moon is, for astronomers, it is easiest to talk about the moon in terms of its age, in the sense that only 4 of the 8 phases actually occur pretty much at a singular point. New moon happens at a particular day or a particular day and time. Full moon happens at a particular day and time. First quarter and third quarter, again, happens on a particular day and time. But all the other phases are very much broadly defined. For example, a gibbous moon, or gibbous, yes, a waxing gibbous, which is what we're seeing here. A gibbous moon, which is sort of more than half, but less than full, that is getting larger day after day. This can go on for about a week. So it's, for astronomers, it's not really all that elegant to say, it's the moon is waxing gibbous. We really refer to it as the age. And right now the age is about 11 days. Now, what does that mean? That means that it is 11 days through its roughly 29-day orbit. And so it takes roughly 1 month or 1 month for the moon to go from, say, new moon through the 8 different phases back down to new moon. And so this is the type of view that you can see basically with your naked eye. You can see these dark stains, which are called mare, and they are ancient. They are very, very old, 4 billion years old, or 4 billion year old lava plains. When the moon was still fairly molten, or the crust had not quite really solidified, large impactors smashed into the moon, broke open its surface, and magma upflowed, and this lava flowed over large or vast regions of the moon, hundreds of kilometers in diameter, or roughly in diameter. Now I'm going to zoom in. Please tell me when you can actually see the zoomed in version.
It seems to be working fine.
Oh, sweet. The other image that we can, or the other feature that you can see, even through a modest magnification, decent pair of binoculars or what have you, the next feature that pops out are the craters, which you can see here. They are essentially the divots. These, I don't know if my cursor's popping up, but those circular areas that look like divots on the surface, those are craters. Those were formed again through impacts, but not nearly as energetic as the ones that formed the mare. And craters come in a few different shapes and sizes, and hopefully we can show you we can show you examples of these differences. Like, for example, a shallow bottom crater, a crater with a central peak, a raid crater, so forth and so on, with using images we've taken here. So is the moon's core similar to the Earth? Olivia, that is a excellent question. And you're in my class, so I think you should know this. But yeah, in a way, yes. The terrestrial worlds are all pretty similar in terms of their structure. There is a core, there is a mantle of lighter material, and that is surrounded by a crust that is even lighter, made up of least dense material. Asking for a friend. So, because all of these worlds, not just the moon, but Earth, well, Earth currently is, but Mercury and so forth, were all geologically active, meaning that there was a magma core surrounded by, or a solid core surrounded by a liquid magma shell, and then a solid crust. And then as the world radiated away its energy, depending on its mass or depending on its size, it would stay geologically active like the Earth, thankfully, or it would become geologically dead like the moon, where the moon's core pretty much is solidified. Most of the magma is now solidified, if not semi-fluid. And so it just becomes this sort of large inert rock. One of the things that is interesting about the moon, or one of the things that is different or unique about the Earth's moon, is that it's off-center. If you looked at any of the other 4 terrestrial worlds, the moon's, the core is pretty much at the center of the entire body. The moon's core is slightly off center, and that is due to the gravitational effect or gravitational influence of the Earth when the moon was forming. That gravitational attraction caused that denser material in the core not only to fall into the center and solidify, but also it did so by pulling it towards the Earth somewhat. All right, so that is the moon. Like I said, it is currently in the waxing phase, waxing gibbous phase. So that means in about 4 days, it will be full. So if the sky is clear on a full, or in 4 days time, then you will see a full moon. Now, when can you see a full moon? That's an excellent question. Full moon is pretty much the opposite of the sun, in that the reason why you see a full moon is because you have the sun here, you have the Earth here, and then you have the moon on the opposite side. And so just as the sun is setting, the moon will rise. Around midnight, the moon will be directly overhead. And then when the sun rises, the moon will be setting. It is actually the only time that you cannot see the moon during the day. Most of the time the moon is orbiting, you can see it at some portion during the day, in the morning or the evening. It depends on the phase of the moon. But I don't want to spend all of my time on the moon tonight. And currently it's in the constellation of Leo. Now, this is a lion. Now, I frequently wonder exactly what the Greek shepherds were imbibing when they came up with these constellations, because, yeah, all right, Leo kind of works. Let's see here. Yeah, so you have the mane of the lion, you have the body, you have the tail, sure. And next constellation I'm going to be talking about is, where are you? Is Orion. And so you have the 3 stars in Orion's belt. Right now, Orion is a winter constellation. So as we move into spring, Orion is going to set earlier and earlier, and we are going to miss out on being able to observe Orion for the next 3-4 months or so until we get into fall, and then it's best observed during the winter.
We're still on Leo at the moment. It froze up, I guess, when you tried to drag it.
Got it. All right. Well, let me know when it pops up again, when it actually gets to Leo. Or Orion, rather. Orion is notable in that most folks that I talk to can identify it via its 3 belt stars. You have 3 stars that are very bright, that are fairly close together in the sky, and they form something of a belt. And then you have 4 stars, 2 stars above that belt and 2 stars below it. And you can kind of see I'm going to put it up, but hopefully it'll catch up soon. You can kind of see that's a dude. It's a hunter. And in a really nice sky, you can actually see an arc of stars to the right of the constellation I talked about. And that's basically a shield or a lion's pelt. And then you can see sort of an arm arcing up from the other side, and that's essentially a club. But a lot of these other constellations, really.
It looks like it's not just, we can see your mouse moving on the screen, but the stellarium window is frozen and like the time is frozen and stuff. It's not just lagging behind.
All right. Let me see if I can bring up. I wonder if it's this. You see it now?
We can see yes. We can see what I assume you're looking at now.
Orion.
Yeah.
Hagrid's
kind of
dragon
a zoomed
cluster.
out view.
Yeah.
Yeah.
Hagrid's dragon cluster. I didn't know that it was a thing. I wonder when that became a thing. Who knows? Let me see if I can keep this because I think it has to do with Zoom. No, probably not. All right. Well, let me really quickly. So that's Orion. Hopefully, this is the 3 stars in a belt. Please let me know when I'm moving around. So I'm going to go to here.
You're on the left side of Orion in our screen.
All right. How about this? How about now? Should be the Orion Nebula.
Yes,
we can
we're
see.
on the nebula.
Sweet. All right. So if you take the 3 stars in the belt, all right, and you go basically towards the horizon, essentially down, you'll see 3 stars that make up his sword. The second one, if you're in a good sky and you have good eyesight, like I used to have, that middle star will appear blurry. And the reason for that is because of the Orion Nebula. And we're going to show you images of the Orion Nebula later on, images that we've taken. Now, there is that star in the middle of that. The reason why it's blurry is because of the massive cloud of dust and gas surrounding the center region. But that star is actually about 3, possibly 4, depending on what your how good your telescope is. Hopefully you can see I moved in quite a bit. And you have 3 stars that are in the center of it. These are referred to as the trapezium. And you can also see the night sky is actually with this. I'm actually going to pause the time. And so what this is, not to steal too much thunder from my GTAs, but what this, in brief, what this is a stellar inertia. These stars are very, very young, only maybe hundreds of thousands or millions of years old. And these 3 that are in the center, which we refer to as the trapezium, these are the first stars that were formed. They are massive, they are blue, they are very, very luminous. And it is that luminosity or that energy being thrown or being generated from these stars that are literally lighting up this cloud that is roughly around 3 light years across. It's a ginormous region of space. Is being lit up very much like a fluorescent light bulb. The energy is smacking into these particles. These particles are getting energized, and then they're releasing energy upon themselves, and you get this lovely field of color and light. Like I said, we'll be talking more about that later on. And that is in the constellation of Orion. Now, let me get to the next one, and then I'll see if I can refresh. All right, where are we? Where is the Pleiades? Oh, right up there. Nope, that's not it. Oh, right over there. All right, so I'm going to do this first. And thank you for your patience while we're doing this. I am at home, and so I am using the Stellarium at home. And for whatever reason, Stellarium is kind of picky when it comes to screen sharing. So can you? Oh, there we go. Can
We're
you
looking
see
at Taurus right now.
Taurus? Thank you. So I'm going to turn off this. So that's the sort of image of what they imagine this grouping of stars looks like. Now I can kind of see it, sort of. If you're looking in the night sky, and the most prominent stars are this V shape where the left upper star is the brightest. And this is actually one of the closest star clusters that we can see, called the Hyades. It is, when I say star cluster, it is a very young collection of stars, not as young as the Orion Nebula, but still a young collection of stars, roughly a few 100 million years old or so. The one thing I want to point out, and right now it's kind of going beneath the tree, behind a tree, is the Pleiades, or the Seven Sisters. I'm going to zoom in and then refresh. That's not what I wanted to do. How about now?
Yep, we see the Pleiades.
Sweet. So as you can see, there are a lot of stars here. In terms of clusters overall, it's actually a fairly small cluster, but because it is close enough to us, around 400 light years away or so, it looks fairly large. It's a naked eye object. It's something you can see with your naked eye. And so if you look in that part of the sky, you would see that's weird. Oh, I just saw the question how big Orion's belt is. Now, so I'll answer that in a second. So with this this cluster of stars, like I said, it's a naked eye object, or naked eye object. You can see a smattering of different stars. It's referred to as the Seven Sisters because at a previous time, when you were talking about astronomers or astrologers who were sort of up and coming or training, one of the things they needed to have is good eyesight. And so the Pleiades were one of these tests. If you could see 7 of those stars inside inside this cluster, then you had very excellent vision. Another test was in the Big Dipper. If you look at the kind of handle where it arches up, that center star is actually a binary called Mizar and Alcor. And again, if you have very excellent vision in a very dark sky, you can actually tell with your naked eye that there are 2 stars really, really close to each other on there. Also, another bit of interesting trivia. The Japanese word for the Pleiades, or the Japanese name for this collection of stars, is Subaru. And if you look at the Subaru logo, one of the reasons why it has one really bright kind of cross, which are supposedly stars, really bright stars, is because the Japanese astronomers noticed a supernova in the Pleiades. And so that big bright star is supposed to represent that supernova. All right, so Olivia has a question. How big is Orion's belt compared to the others? Are you talking about how big the stars in Orion's belt are, or just the size of the Orion's belt with relation to the rest of the constellation?
The size of the belt compared to the other.
So let me go back and then I will refresh. All right. Can you all see Orion?
Yes.
All right, so Orion's belt is here. So you have the 3 stars on the Orion's belt. You have the 3 stars in his sword. You have the shoulders, Betelgeuse being the upper right, Rigel being his lower left knee, and that one here. So it's comparatively small, but it's distinctive, because if you were to look up in the night sky, there really is no combination of 3 stars in a line this bright. Particularly once you know what to look for, it is striking. You'll never be able to not see it if it's up on night sky. Let's go on. So I wanted to talk about that, and I also wanted to talk about I'm going to zoom in here. Where is, oh, there it is. All right, I'm going to first show this. Hopefully you can see Taurus again.
Yes.
All right. So I talked about that V shape. There's Aldebaran. That's the big bright one in the upper left of the V. You have this one, that one, and then that one that can be easily seen. If you look much farther away, talking a few degrees away or more, you have two really pointy stars up here, which correspond to the top of the horns. Now this little bit here, which is basically I've highlighted. Let me center in on that. I showed you the Orion Nebula, which essentially is a location where stars are born. Now, ultimately, as I've been talking about in my class, my 103 class, stars will eventually run out of fuel. Will eventually not be able to burn or create energy anymore, and then they will collapse and they will die, and they will become morbidly, they would become a corpse. So one of these objects is called the Crab Nebula. And it's also known as M1, or the first object in the Messier catalog. Now, just as a brief aside, the reason why the Messier catalog exists is because of Charles Messier, who was a French astronomer late in the 1700s. So one of the first things to be in vogue with astronomy was looking at comets. Comets were fairly obvious in the night sky, and they were sort of ubiquitous to this idea of the Earth coming to an end and so forth and so on. And for works of art will sometimes have comets trailing over important events. The one that comes to mind is the Battle of Hastings. In England, there was a bright comet that could be seen during that battle. So Charles Messier decided to throw his hat into the ring, and he wanted to find comets like his compatriots. But history has not remembered if he actually discovered any comets whatsoever. It does remember the stuff he wrote down that were not comets. So he could see a whole bunch of fuzzy blobs in the sky, and that literally, because his telescope wasn't great, they were literally fuzzy blobs. And he noticed there were fuzzy blobs that did not move, and so they could not be comets. And so, because I guess he didn't want to keep finding them again and getting his hopes up that this was a comet, he decided, I'm going to write all this down, and I'm going to essentially no longer look in those areas because that's not a comet. That's not what I'm looking for. M1 is the Crab Nebula. Hopefully you can see that.
Yep.
And again, not to steal my DJ's thunder, they will be showing you images that we've taken with this. But this is what we refer to as a supernova remnant. And so you have a massive star like the ones in Orion that I talked about in that trapezium area that were lighting up the entire Orion Nebula. One of those stars, or any of those stars really, they're going to eventually burn through their nuclear fuel, and they're going to collapse, and they're going to explode as a supernova. And they're going to leave behind either a neutron star or a black hole. I think in this case, there is a neutron star remnant. There isn't, I don't believe that there's a black hole in the center of this nebula. And we can see that the stuff that's surrounding it is ultimately the body of the star, the stellar envelope, the outer most of the star exploded outward very, very violently, and is now traveling through space at hundreds of kilometers per second. And it has these beautiful colors because of the different chemical components or chemical elements that are inside of it. Again, we will be showing you images of, actually, I would say, if I might be so bold, I'd say they're fairly on par with the one that we have here. The Crab Nebula is one of my favoriteest images to look at, particularly to image, really because it's kind of easy to do, comparatively speaking. All right, how am I running on time?
It's about 7:38.
7:38. All right, so the moon. What else did I want to talk about? Okay, one of the things I want to talk about, because it's actually something that will be it'll be a while before it no longer is visible. And if you have a good pair of binoculars, you can actually see it. And that is, and I'll zoom in a little bit. Something like that. All right, so this, actually, let me zoom out real quick. Hopefully you can see the bright night sky with the various constellations. Yes, no. I'm going to
Yes, we can.
Yeah.
That's a yes.
Sorry.
So we have Leo, obviously over here. You have the moon. You have Gemini. You have Orion down here. I'm going to scroll up. Hopefully this doesn't. This still works. You have the Big Dipper, which is referred to as Ursa Majoris. That's the main constellation. But if you take a smaller subsample of stars known as an asterism, you get what is popularly known as the Big Dipper. So you have these 3 stars in the handle, and then you have these 4 stars in the belt, or excuse me, in the bowl. And then these 2 stars, incidentally, if you took the 2 stars at the end of the bowl and you went north towards them, you would actually find the North Star Polaris. So if you can find the Big Dipper, and you can figure out when it's up sufficiently high enough in the air, and you can find the 2 stars at the edge of the bowl, you can follow those along down towards north, or up towards north, over towards north, and you should be able to see the North Star, which is not overly impressive. It's visible, but it's not one of the brightest things in the night sky. But it is certainly the brightest thing in that region of space. In the night sky that we have here on our campus, it really is the only thing within a few tens of degrees around it. It's significant in that way. But what I'm going to be focusing on is the Crab Nebula, or excuse me, what I'm going to be focusing on is the constellation of Cancer, which is a crab, and I'm going to be talking about the Beehive Cluster. Now, this is a great example of how is this supposed to look like a crab. I have no idea. It's this. Let me zoom in a little bit more. No clue how this arrangement of stars looks like a crab to anybody. But the Beehive Cluster, if you can find this, if you can actually, I would suggest using a star app to do this, which there are many on the market that are free. Basically, find the Beehive Cluster and find the constellation of Cancer, and right in the center of it is the Beehive Cluster. I'm going to zoom in. And restart. You have the Beehive Cluster, which is a older star cluster, and again, it's very close to us, so we can see a lot of its constituent components. And like I said, you can see it with a pair of binoculars, and you will. It is unmistakable in the sense, if you have your binoculars and you're looking around in that area, you'll see a few stars, and once you get onto it, bam, you will see a whole lot of stars in a really small area, and that is the Beehive Cluster. And the last thing I'll say about the Beehive Cluster is I want to send a shout out to a friend of mine, guy I went to grad school with, Sam Quinn, who is now working, I think, at BU. He found exoplanets, 2 exoplanets around 2 stars in this cluster, using a telescope very similar to the one that we use today, or the one that we use here at George Mason. So we can use our setup. We do use our setup to look for planets around other stars. Yes, it's definitely missing a few legs, maybe a couple of pinchers. But yes. So, all right, with that, I think I'm going to stop rambling. It's definitely, I was going to say it's still bright outside, but it's cloudy, so it doesn't matter. I will turn it over to Em and Kevin, and they will walk you through the telescope itself, talk about the specifics of its optics, its size, so on and so forth, the camera that we use to take images, and show you a few images of a few of the items, of objects that I have highlighted this evening. So again, if you have any questions for me, I will be sticking around, so please put them in the chat. If you have any questions, if you're one of my students, you'll probably be here for the observing report. If you have any questions about that, again, put those in the chat and we will answer them as soon as we can. So with that, I am going to stop sharing my really slow screen.
All right.
And I will hand it over.
Thank you very much. Let me share the desktop. All right. Can you see the webcams now? Great.
Yes, I can see.
All right. Well, welcome again, everybody, to the GMU Observatory. Here you can see 4 live camera views of the observatory itself on the roof of Research Hall. I'd like to also start by inviting you all to come back again. As was mentioned before, we have one more Evening Under the Stars event this semester. That's in 2 weeks, which I believe is April 26th. It will also be at 7 p.m. And virtually through this same link. I also don't know the specific subject of the talk yet, but it will probably have to do with black holes or active galactic nuclei or something of that nature. Look out on our website or Facebook or Twitter to find out more information about that. And then also, hopefully, assuming that things continue to improve in the COVID-19 landscape, we do intend potentially in the fall to open these back up to being in-person events. So I'd like to invite you all to come back and see us in person for a talk and actually come onto the roof yourselves and actually get to look through.
My audio just tweaked.
Okay, thank you for muting. But yes, I'd like to invite you all back in person and perhaps on another clear night. You might even get to look through the eyepiece itself for a live view at the night sky, which is really, can't really be substituted through Zoom. Anyway, you see here these 4 camera views. In the top right, we have a view of our control room. Obviously, no one's there right now as we are able to control the computer remotely. There's a desk with a computer on the left-hand side that you can, is actually the one that we're looking through right now, the desktop that we're looking at. And before the pandemic, you did have to physically be in the room to control the telescope, but that accelerated our plans to kind of automate things and go remotely. In the top left, we have the main feature, telescope itself. It is a 32-inch Ritchie-Cretan Cassegrain reflecting telescope. For the question in the chat. Now, what all those words mean is basically just describing the optics of the telescope and the path the light takes to get to your eye or the camera that we use. And so it's a reflecting telescope instead of a refracting telescope. And the difference between those two is whether or not it uses lenses or mirrors. So this telescope and many large telescopes like it, research telescopes, use mirrors instead of lenses because they're you can make them much cheaper than a big glass lens, and they're also much lighter, which is important when you're moving around delicate optics and multiple thousands of pounds of machinery. So the light enters obviously through the front end of the tube of the telescope. It bounces off the primary mirror in the back, which is in this black housing here at the back that's 32 inches across. It reflects the light back up out of the tube, but it hits a secondary mirror that's about a foot across at the front end, which then reflects the light and focuses it back down through a hole in the primary mirror. before being redirected by 1/3 and final mirror into whatever instrument we want to look at the stars with, either a CCD camera, which we use for our research observing and astrophotography and other remote observing, or an eyepiece if we want to physically look through the telescope, just like a backyard telescope. And we also have a low resolution spectrograph on the back as well that we could use if we want to split up the light from the star into different wavelengths, into its different components, kind of like a prism, which you can use to identify the composition of something that you're looking at. And in a minute, I'll also move the telescope around a bit so we can get a better look both at the mirrors and at some of the instruments on the back. Checking the chat. I said reflecting telescope is what we use. Now, in the bottom left, obviously, we have the observatory dome itself that houses the telescope. For scale, the door is, I guess, about 6.5 feet or so, and the dome is about 20 feet across. So it's a pretty sizable structure. It's pretty easy to, it's pretty noticeable if you're walking on campus by Research Hall. Just look up and maybe on a dark night, you'll see it rotating around as we're doing some observing. And the bottom right view is one of the two motors that are used to turn the telescope, to move it throughout the sky. This one in the view on the bottom right twists the fork that the telescope's mounted in. And then the other one you can see at the top of the fork up here rotates the telescope kind of up and down in the vertical direction. And between those two, we can point almost anywhere in the night sky. So now, this is the software that we use to actually point the telescope. This is a night sky view, sort of similar to the stellarium that we were looking at earlier, except it's connected to some machinery. We can point and click if we want to go to a specific location in the sky, and we can tell it to move. And if we go back to the cameras, we will see telescope in the top left. There we go. Starting to come into view towards us. Just let that go for a minute. Checking out the chat. Thanks, Em and Dr. Parks for answering some questions. Those not keeping track of the chat, the aperture is 32 inches across, and that corresponds to the size of the primary mirror. And that is basically just indicative of the light gathering power of a telescope. Often when people are asking about telescopes, they ask about things like the magnification, how zoomed in you can look, but astronomers are really not that interested in the magnification. What's more important to them is the light gathering power. So the question isn't really how small of a thing you can see or how far away it is. What's more important is how faint of an object you can see, because that sort of determines the your sensitivity. Let me go just a little bit lower here. And the primary mirror will come into view, just barely. You can see the secondary mirror assembly here at the front. This is the back of the mirror that reflects the light and focuses it back down towards the base. And we'll probably just see the very top of the primary mirror coming into view. There you go. And there's actually a small hole. The primary mirror is shaped like a donut to allow the light to pass through the center of it and get reflected to our research instruments. Okay. No, it's still looking pretty terrible outside, but I will, just in case, we'll go ahead and point it at the moon. And we won't be able to take an image or anything yet right now, but we can watch that yellow bullseye is the current location of the telescope. And that obviously we can correspond to webcams to make sure things are going where we think they should. Maybe in a bit, when it gets a little darker, we can try taking an image anyway. It probably won't work because there'll be clouds in the way, but who knows, maybe there'll be a slight hole in the sky and we'll get lucky. Anyway, for now, instead, I will show you an image of the moon that we have taken with the telescope in the past. All right, so here we go. Zoom that in a little bit. So here you can see the moon kind of fills up our entire CCD detector. The field of view is about 26 arc minutes across, which is a little bit less than half a degree. And that means that we can only fit about maybe 2/3 or so of the moon in the camera at the same time. And you can see highlights some of the features that Dr. Parks was talking about. We have the dark mare, the long billions years ago cooled lava plains from ancient lava flows on the moon. We've got the brighter highlands that are covered in many craters. And we've got some interesting facts about the moon that weren't already covered. So the moon is quite old. It's about 4.5 billion years old or so. The prevailing theory about the formation of the moon is that the Earth was long ago struck by another ancient protoplanet. I believe they refer to it as Theia. And it was about the size of Mars, and it crashed into the Earth over 4 billion years ago and ejected a bunch of debris into orbit, which then coalesced to form the moon. Now, this view that we have from the telescope here looks relatively flat. You really can't make out a ton of detail. We look at another image we've taken. You can see a lot of interesting features along this line here where it goes between day side and night side. That line is called the terminator. And it's definitely always the best place to see sharp details on the moon. So if you're looking at the night sky, if you've got a pair of binoculars or your own telescope, it's much nicer to look at the moon actually when it's not full, because then you get that sharp contrast in the craters and things, and you can make out a lot more detail. Let's see. For now, I think I'll pass it over to M for a bit, who will show us a couple more objects.
Okay, so we discussed about the nebula. Remember the Orion nebula. So let's see if we have that. Okay, so we have a color image of Orion nebula taken by our telescope. So I think you can maybe see some difference between this and some pre-recorded image on the stellarium. We cannot really see the bright spots at the core of this nebula. But it can still give us some details about this nebula. We can see the dark cloud of dust that blocked the light. So this nebula is what we call reflective nebula. It scattered light from those protoplanets, protostars, and there are a lot of newborn stars forming inside those cloud of dust particle and hydrogen, helium. I'm not sure if we have other images of Orion Nebula. This is another image of Orion Nebula. I'm not sure which are the filters we use. So in order to produce a color image like this one, we use several images recording with some different filters, and then we combined those filters. For example, you may have heard about the red, green, blue pixels on your computers. So on your computer screen or your camera phone, I'm not sure why my VNC, the program is keep bouncing. Okay, so when you see those images on your computer screen and the camera, it's actually a combination of colors. Like if it's the image shown on your computer screen or phone, it's made of red image, blue image, and green image combined. But in astronomy, we can select a specific type of filter. Maybe we can look at the infrared and maybe green light. We call it vision, and maybe ultraviolet. And then we assign some color to those filter and combined, okay, in order to see some different structure inside within the same object. Okay, so comparing to this image, we can see those bright stars very clearly, but we do sacrifice some of the cloud outside, and maybe this is due to the exposure time of the image also. We can choose whether we point the telescope at this object either for a long time or short time in order to collect the appropriate amount of light on this image. Okay, the next object is crab. Still nebula. Crab nebula. Should be M1. Oh, we'll name it crab. So this is recorded in visible light, RGB, red, green, and blue filter. So as Dr. Park explained, it's a remnant of the supernova remnant. This formed about 1,000 years ago. It's noticed by Chinese people in that time. I think it lasts around 3 months. They see this actual supernova, and it was recorded that people can actually see the supernova during daytime for about 3 weeks. And at the core of this crab nebula lies a pulsar, and we believe it's a neutron star. So those reddish wave, it's like the shock wave of the remnant of that exploded star expanding to the space. Okay. And fun fact about this object, it's the only supernova, I believe it's the only supernova in Charles Messier's catalog out of his 120. this is the only object that is the supernova remnant. Okay. I think we still have no luck for our sky. So maybe I can show you a little bit more of our recorded image.
You could probably open up. I don't think there's a chance of rain. Who knows? We might actually get something in the note.
Okay, yeah. So let me open the dome. So Kelvin showed you how we can control the telescope. We can also control the dome using this program. I just click open. And we can see its window sliding up. This may take about 5 minutes, I believe, to fully open the dome. Okay, so this will retract this way, and we should be able to slew the dome, we said slate the dome, which is synchronized with our telescope. Okay. While we are waiting for that, I'll show you another, this is called a planetary nebula. It's a remnant of an exploding star also. I cannot actually tell, but usually those kind of planetary nebula, we can see the bright spot at the center, which is white dwarf, the remnant of exploding stars there. It used to be a core of a star, while the rest of this is just the outer shell. Okay. This one is called bubble nebula. As you can see, it's like there is some hole inside this cloud. And we have about we recorded in two arrangements of filter. This one is recorded in hydrogen alpha and red and visual filters. Hydrogen alpha is a specific wavelength produced by hydrogen. Its color is about so the color of this wavelength is corresponding to somewhere in the red spectrum, and we combined it with the red filter and also the visual filter, which is about in green spectrum, I believe. And those three combine to form the color of this image. It looks a little bit different from this image. Not sure about this filter. So I hope this can give you some ideas about how we can make different color image using different filter for astrophotography.
Yeah, I think I mentioned before when I was talking or showing some of
Okay.
Owen's work. Astrophotography is difficult, particularly this type of astrophotography, when you're talking about taking images in 3 different filters, unlike DSLRs, which can take a color image, you strap that on the back of a telescope, take a color image, and boom. We actually have to take images in 3 different filters and then figure out a way to properly combine their light so that we get an accurate image, or accurate 3-color image. And yeah, it's not easy in any shape or form.
And now I slave the dome to the telescope, which is just basically aligning the dome so that this window is pointing at the same direction as this telescope. Okay, should we try capture the moon?
We can give it a go. I don't see why not. It's
Yeah.
probably just going to be clouds, but we're already on it, so might as
Yeah,
well
we're
take an
already on it.
exposure.
Yeah, the moon's pretty bright, so who knows?
So
I would only
Sure.
do a second in visual or what have you.
So we use a program called MaximDL to control the camera, the CCD camera of the telescope. Right now we have some focus position. It's actually a random number that correspond to the actual mechanism of the focus. We move the mirror of the tertiary the tertiary mirror. Oh no, not the tertiary mirror. It's a secondary mirror in or out based on this value. So Kevin, you controlling the screen, right? Okay.
Yeah, I just started an exposure.
Okay, so we're recording the moon in red filter using 1 second exposure time.
Hey,
Oh,
there it is.
there's something.
Oh.
Yeah, that's the moon.
That is the moon. Have to play with the screen stretch, but
Yeah, so let's see here. Moon.
moon setting.
Wonderful. That's much better than I was expecting, actually. So there's a live view of the moon. It's not the best image we've ever gotten, but not bad at all.
Maybe it's inside a hole of the cloud.
Maybe.
The sky does appear to be opening up a little bit, so yeah. And it's very bright, so.
Yeah, I can actually make that exposure time less. Let's do a half a second.
It's true. It's probably why it's so washed out at the bottom, is that we have overexposed. We have gotten, we have collected the maximum amount of light the camera will allow in the bottom of that image.
That's one. Oh, there are
Oh,
clearly
there's
clouds
definitely
above.
By the cloud.
Yeah, but that is one major advantage, obviously, of using a telescope with a camera on it instead of looking through with your naked eye. The things you can see are very different. Your eye can only essentially let in so much light at a time before sending that information to your brain. So the quote unquote exposure time of your eye, though it's a little more biologically complicated than that, is only about like a 15th of a second or so. Whereas we can leave the shutter open, exposing on our CCD camera for essentially as long as we want, though we usually don't go more than a few minutes. That's still vastly more light that we are letting into the sensor than gets let into your eye at a time before getting sent into your brain. And that's the reason that camera left on a long exposure can see things much, much dimmer than things you can see with your naked eye.
All right, I'm fiddling with things. I'm trying to come up with a continuous refreshed images, but the screen stretch is not accommodating me today. Wow. All right, that's really blown out. So I think it's no longer in any sort of cloud, or for this image anyway.
Should we also shift the camera or the telescope a little bit left so we can see the Terminator line?
Terminator is, yeah, we could do that. That's fine.
Yeah.
Oh, wow, it's really, let's do this. It is really bright now. Let's try that.
We can bump it down to 1/10 of a second too if we need to.
Yeah, but I think it's still going to be, that may still be too bright. There we go. Mwah.
Wonderful.
Perfecto.
Okay, I guess I'll move the telescope over a bit. Go a little bit left. And now take a new exposure, and I'm going to try doing the continuous now and see how it likes that. Hopefully I moved it in the right direction. Sometimes up and down or left and right or flipped, and it's, I don't remember which. Yeah, wrong way. Okay,
Oh, yeah, I should have been able to. Yeah,
that's fine.
left and
We'll just
right
go
are fine.
clicks.
Left and right actually go left. The object goes left and right. Up and down is flipped.
Got it. Okay, well, our next exposure will probably look ridiculous because the telescope was moving during it, but that's fine. Something in the chat. Oh, you got it. Yeah, we are indeed looking at the moon. All right.
Right. Yeah.
That's another decent view. Well, before the
Wow.
clouds.
For those of you who are wondering what I did to get this nice images, I put it on the ultraviolet filter, which we get the least amount of light through it. And so you actually, with the other filters, the moon is so bright that we can't close the shutter fast enough before we get too much light. But in the ultraviolet, we can keep the shutter open half a second and still get the right amount of light so that we can actually see what we're looking at. Now, you might be one of the more recognizable thing, so you have the Mare, but the most recognized crater in this image that you're currently seeing is the one right just next to, well, I'll just do this right over here. Hold on, let's see if does my cursor actually show up?
Yes.
Right where that spinning thing is. That is the crater Copernicus. Oh. And it is a raid, what we refer to as a raid crater. Bring that back up. I ain't touching it. Maybe minimize the sky.
Yes, that would work too.
It is called what we call a raid crater. Is because if you see, if you look closely enough, there are light rays or white spokes that come off of it, very much like a child's drawing of the sun. And what that is there a lighter colored material just kind of low beneath the crust that gets expelled when that impact happens. That impact happens and causes a fairly violent explosion, and it dredges up this lighter material and just sprays it out like a ray, like rays from the sun. So that is Copernicus.
Well, it looks like in the webcam that things are clearing up a little bit.
It does.
Yeah.
It does.
At least to the west. I don't know if there's more clouds in the south or something, but we could maybe try the Orion Nebula if you wanted to.
Yeah. Why not?
Why not? Just gotta. Okay. So we will move over to the Orion Nebula and hope we get lucky. Oh, it's pretty far elsewhere in the sky, so we won't be looking through the same hole in the clouds, but who knows?
It's also lower down on the in the sky, and so we're looking through more atmosphere. So it's going to be more blurry than if it were up near the top of the atmosphere or top of the sky.
I guess also more likely that there are clouds in the way. I guess I can show the webcam view so we can watch the.
This is Sunny. She was the one stuck in the mattress.
Hi.
Blah, 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 blah.
In the chat, the proper name of one object viewed through the telescope is the moon.
Moon.
Or Luna, or I'm sure hundreds of other names, if not thousands. All right. Pretty far move.
Film to catch up.
Finger crossed. Hope it's not in the cloud.
Indeed. There goes the dome. Let's see. We'll go ahead and move
That's
this
a
back to-
That's a question from the chat. All of our equipment wasn't remote controlled until recently, correct?
Okay, if you want to take that.
Yeah, I think it's since COVID, we just installed those
summer of
cameras.
2020.
Yeah.
Remote observing got underway.
Yeah, it was on the to-do list for a while, and then the pandemic really forced us to up that timetable. So sort of a silver lining to the whole thing. It prompted us to make this remote far quicker than we probably would have ordinarily.
Right. I see some clouds out the slit in the dome, but we will hope for the best.
Mhm. Yes, we had some excellent grad students who and an undergraduate who wrote a lot of the code for helping things get automated. And so, yes, it was definitely a tremendous effort to get this where it is today.
I think Kevin also used it for his research, right?
Yes. So,
automated.
right. On every clear night, the telescope is used. We use it for obviously this event, events like it, Evening Under the Stars, other public events, and we do private tours to the public. Oh, wonderful. We've got Rob, I'll let you fiddle with the image. We also have tours for intro undergrad astronomy labs, astronomy 112 and 114 primarily. And then on every clear night after those things are done, we do active research with the campus telescope. We look for transiting exoplanets, which are planets around stars other than our sun that pass between us and their star, so that we can essentially see the shadows that they leave. And we can measure that to actually confirm a planetary signal on something that is much, much too small and dim to actually see directly. And we have been successful helping confirm a decent number of planets at this point. And that is ongoing essentially every clear night. All right, we have the Orion Nebula here. It looks pretty good, all things considered. Obviously,
Yeah.
it's a bit blurry, washed out a bit. The focus isn't great. But yeah.
Yeah, this isn't the best image we've ever taken, but if you scale things right, basically use this histogram tool, you can basically highlight various features. So if we use this particular tool, what we're doing is we're highlighting the extended or batwing sort of nebulosity. You can kind of see a companion nebula up here, and then you have the trapezium. But if we don't do that, we primarily just get a much better look at the central region of the nebula, like so, which is the trapezium. Nicholas, yes, you can. It is all right.
And I guess, again, this was touched on before by both of you as far as astrophotography and combining to make color images is concerned. But as you can see here, obviously, the pictures that come in from our CCD camera are all in black and white. There is no color information. It's essentially just counting the photons that hit the detector, where they hit the detector, and it's just adding them all up. And so you essentially get a grid of numbers. And then this manipulation that's being done with the stretch isn't actually doing anything to the underlying data. We're basically just telling the program what to assign to black and what to assign to white, and everything in between gets assigned a certain shade of gray. And we can manipulate that scale basically to bring out those different features we were talking about. Yeah, I think this is a success. And I think if we tried to take another image based on webcam view, it would not be successful. Got real lucky there. Well, Dr. Parks, unless you have more, I think that's probably about all for me.
Yeah, I don't, given the sky conditions, I don't believe we can really show you anything. And again, for one, I suppose if you, again, have any questions, astronomy related, telescope, observatory related, astrophotography related. Oh, I would be remiss in not mentioning that right now we are celebrating International Dark Skies. And so the astronomical community is focused on, from a public outreach perspective, is focused on trying to get the night sky as dark as possible. Now, obviously, in metro areas, that's a big ask. But in smaller communities, we can potentially mitigate the problem of light pollution, of urban light pollution. And really, it's more of yes, International Dark Sky Week. Thank you, Kelvin. And what we're trying to do is get ordinances passed, and it's not only just for astronomy, but really it's for people. We spend a lot of energy putting light up in the sky where we don't need it, and so it's just simple fixes to change filters, change fixtures, so that the light is streaming downward as opposed to just everywhere. Okay, just real quick, what do you do for the attendance? Take a screen grab of, well, this, and that pretty much proves the attendance. So one of the, before we close out, just in relation to International Dark Sky Week, we at the university are currently looking into ways to mitigate the light pollution on our campus, because there is, particularly in the northern and western parts of the sky, there is a significant amount of light pollution simply from the campus itself. There are two pillars, if you're familiar with Enterprise and the Enterprise and Research Hall, you might notice two pillars that are giant light sources that if they happen to get shot out, I had nothing to do with it. So those are the types of examples of light pollution that we're talking about. It's purely decorative. It doesn't need to be there, and we're hoping to be able to mitigate it in some way. So yes, and it has light pollution also affects nature itself. It affects the life. It affects what's the word I'm looking for? Essentially, the night-day behavior of animals, of insects, things like that, of that nature. Nature likes a diurnal cycle, clear distinction between day and night, and with light pollution, it really disrupts that that cycle. So, with that out of the way, what I'd again, I will give you this opportunity to ask any questions, and if not, then we will bid you adieu and wish you all a good night and a good week. Field of view is 25, 26 arc minutes. Thank you all. What is the proper name of one object viewed through the telescope? That would be the moon.
The moon with capital M.
Yes.
Yeah.
The moon. We
Proper
shall
noun.
steal the moon. All right, folks. Again, I'm going to sign off now. So have a good one. Let me end this. Peace out.